I want to take this little small lecture and just deal with carboxylic acid derivatives, its nomenclature and properties. Carboxylic acids, as I said previously, also is a huge chapter because carboxylic acid is a huge functional group, not by itself, but because of the derivatives that we have, which means that we also have to do reactions and synthesis of all those derivatives. So in this one, we'll just talk about nomenclature and properties, and we'll deal with synthesis and reactions in another one. So the derivatives of carboxylic acids are right here. Okay, there's a whole lot of derivatives here. Carboxylic acid is one. Okay, it's not shown here, but carboxylic acid is also one of the derivatives of carboxylic acid. And then here is acyl chlorides. Okay, right here, you see the carbonyl is always there. All right, the carbonyl is always there except for the nitrile. All right, but things on the right hand side are changing a little bit. So instead of the OH group, here we have the Cl, that's called an acyl chloride. Here we have another whole group here, which is kind of, if you think about it, a mirror of the left side, okay, which we will talk about later. And this is called an acid anhydride. And esters you already learned in organic 1 as a functional group because these are fairly stable compounds. And so this is OR over here. Nitrile is one of the most unusual functional groups of or derivatives of carboxylic acid because there is no oxygen in it. Okay, it's just triple bond nitrogen. And CN in organic chemistry is called cyano or cyanide, but organic it's called nitrile. And then here are the amides, and the amides are 3 over here only because of the different alkyl groups on the nitrogen, not because the amide group is different. The amide group is known from the carbon double bond and nitrogen. That's it. Okay, whatever else is attached to nitrogen, that's fine. It could be hydrogen or alkyl groups. It's still an amide. So for acyl chlorides in the nomenclature, this is very simple, and again, we'll try not to make it too complicated, okay? So remember the acyl group is RCO group, okay? So that's an acyl group in general, okay? That's how we call it. So in case of acid chlorides or in acyl chlorides, you will drop the ic acid and use il chloride. All right, so for example, in case of ethanoic acid, which have been acetic acid, it will be called ethanoyl chloride or acetyl chloride. Acetyl is coming from acetic acid. Okay, so acetyl chloride. And then from benzoic acid, it will be called benzoyl chloride. Hexane dioyl chloride is coming from the fact that you have 6 carbons over here, and then the carboxylic acids would have been over here. And so it's dioyl also because you have 2 acyl groups, 2 acyl chlorides instead of just 1. So that's hexane dioyl chloride. All right. Some of the properties are given also over here. I'm not going to go over very much separately with the properties of acyl chloride. There's a table at the end, but I'll just deal with it a little bit now also. Okay, and so acyl chlorides have a higher boiling point, not too high, but relatively good boiling points, which means that they're all liquids at room temperature. And they have a very strong smell, really pungent, even worse than acids, I would say. All right, so that's kind of what it is. They're highly soluble in water. We'll talk about that later also, but those are some of the properties of acyl chlorides. For esters, the naming is based on the carboxylic acid and the alcohol. Okay, carboxylic acids are made from alcohol and acid. So the pink color over here, that is coming from the alcohol, and the carbonyl part is coming from the acid. Okay, so that is how you differentiate. Of course, I won't give you color coded, but the carbonyl carbon is coming from the acid. That's how you will differentiate between what is coming from the alcohol and what is coming from the acid. Okay, so whatever has the carbonyl group, that is coming from the acid. Obviously, alcohols don't have carbonyl groups. Okay, so naming the carboxylic acids is like naming salts that we've learned previously in the acid chapter, and which means that you name the alcohol first, which is kind of like a cation, all right, because we consider esters to be like an acid-base reaction, all right, so alcohol is considered to be like the cation, and then the acid part will be named as an ate. Okay, so for example, in this case, the first one, here we have an ethyl group, so this is ethyl, and then the fragment from the acid is ethanoic, is coming from ethanoic acid, so it's ethyl ethanoate or ethyl acetate. Okay, so it has to be ending in ate. As soon as you end it in ate, you know you have an ester. Okay, and so there's no name as an ester. All right, so it ends in ate. Here is another group, and again, don't be scared by the bulkiness of this group. It's just a T-butyl group. So T-butyl propanoate. Okay, that's what it would be called. And then this one here would be the vinyl group, so vinyl ethanoate. So keep it simple. Name the alcohol first, and then you name the acid fragment. Okay, so here is some with the benzene, okay, as your main structure, so which means that we're talking about benzoic acid. So here, in case of these kind of substituents, all right, you would name the methyl still first, okay, because it's the cation. So methyl, whatever is attached from the alcohol is named first. So methyl parachlorobenzoate. So whatever is on the carboxylic acid, okay, on the oxygen here, that will go first always. Okay, this one is coming from a diacid, so this is diethyl malonate, and malonate is diacid. But in any case, hopefully you will not have to work with so many of the diacids or diesters. Okay, you might deal with benzoates, but not so much with the diacids. Now, the esters are actually internal groups. Internal groups meaning that you find them inside two carbons, okay, or you find them surrounded by two carbons. So if you find anything surrounded by two carbons, just like ethers and ketones, you can also exist as a cyclic compound, okay, and the cyclic esters are called lactones. Very specifically, they're called lactones. So here is an ester, okay, so here is the carbonyl carbon oxygen. Here is the other oxygen, and here's the carbon. And so this is really what makes this an ester, okay? So you will not call this a ketone, and you will not call this an ether, because that's not what this is, okay? If they're right next to each other in a ring, then they would be an ester group, okay? And an ester, again, cyclic compounds are known as lactones. The lactones are known by their ring sizes, and the way you start doing the ring size is alpha, beta. The alpha carbon, again, remember, is the one next to the carbonyl carbon. So that's alpha. So how many number of carbons you have is how you determine what kind of a lactone you have. So in this case, this is alpha beta, so this is beta lactone. Okay, don't worry about the butyl part. As soon as you know that there is a beta, that means you know that you have only two carbons. Okay, so that's how it works. This one is alpha, beta, gamma. This is a gamma lactone, and this is an epsilon. Okay, and so that's how you kind of know what kind of a size you have of the ring. If you wanted to do the IUPAC way, then you would start with number 1 as your carbonyl carbon, because in IUPAC you have to account for all the carbons. So start with 1, 2, 3. So 3 lactone or 4 lactone here in this case, and in this case it will be 6 lactone. Okay, so that's how you make lactones, and again lactones are cyclic esters. Now for the anhydrides. Anhydride means without water, and means without, hydride means water, so without water. So this is actually made from dehydrating 2 carboxylic acids. The 2 carboxylic acids can be 2 separate acids or a diacid, okay, and so that depends on what you're trying to make, and we'll talk about that later. But anyhow, the nomenclature of anhydrides: whatever the one fragment is, that is what you take as your base, and then you just call it anhydride, especially if it is a symmetric anhydride. So for example, in this case, look at the carbonyl carbon. That is what you're looking for. That's what you're focusing on, okay? I know there are too many oxygens to look at, but focus on the carbonyl carbon and then fragment it into half, okay? And then see how many carbons you have on either side. And you will see that you have 2 carbons, and so which means it's coming from acetic acid, which means this is then acetic anhydride or ethanoic anhydride. So you keep the ic, okay, in this case. So acetic anhydride or ethanoic anhydride, all right, that's what this is. These anhydrides that you see over here, these are actually coming from diacids, because anhydrides are internal groups. How? Because they are between 2 carbons. So if something is between 2 carbons, you can have an internal functional group. So here, if this was a diacid, the diacid here would be 4 carbons. 1, 2, 3, 4. A 4-carbon diacid is succinic acid. And so if you remove water from there, this is what's going to happen. It will form a ring, and that's called succinic anhydride. Okay, and this is phthalic anhydride, which is phthalic acid, in which case you have not benzoic acid, a benzene ring with 2 acids ortho to each other. And so those two, if you dehydrate, you will get this anhydride, which is phthalic anhydride. Here is maleic anhydride. So in any cases, these are all anhydrides. Typically, you are given the structure of the anhydride. You may not have to memorize all of them. You will encounter maleic anhydride. You've already encountered it before in Diels-Alder reactions. Okay, and so acetic anhydride you may have also seen before. Anhydrides are very stinky compounds also, just like acyl chlorides. Okay, coming to amides. Amides are made from acid and amine. This is kind of a very typical acid-base reaction, and this is organic acid, this is organic base, and that leads to amides, which is a functional group of an acid, but you also learned of amides as a separate functional group, okay? But essentially they are a derivative of carboxylic acids. So in this case, when you name the amide, you would drop the oic acid and replace it with amide. Now remember the amides, okay? They are different because you can have several groups on, or not several, 1 or 2 alkyl groups on the nitrogen. So the simple ones are very simple to name. You just look at whatever your base chain is. So here in this case, you have 2 carbons. So this would be ethanamide. Okay, ethanamide, ethane coming from 2 carbons and then amide. Okay, that's exactly what we're doing. And then the general name would be acetamide, acid coming from the 2-carbon fragment here, all right? If you have some groups on the nitrogen, then you have to mention those also. So this would be then N,N-dimethyl acetamide or N,N-dimethyl ethanamide, all right? The N,N-dimethyl, you have to mention the N,N twice, and you also have to mention the di. Okay, you can't get away with any of these two. All right, just because you say one N in there doesn't mean that you've accounted for both, because you can also have methyl groups on the chain here. Okay, and so you want to specify that the methyl groups you're talking about are actually attached to the nitrogen. All right, so N,N-dimethyl acetamide or N,N-dimethyl ethanamide. And then here we have N-ethyl ethanamide, okay, where you have just one group. So again, just one N over here is good enough, all right, for that. Here are some more examples. So here we have N-phenyl, N-propyl, and then ethanamide, acetamide. Benzamide is very simple, coming from benzoic acid and then amide, okay, benzamide. Amides are what we call internal groups also, and so which means you can find them in cyclic structures, okay? And this is what makes this functional group of carboxylic acids and its derivatives really huge, because not only are you dealing with the straight chain compounds, you're also dealing with the cyclic derivatives, okay? So just like esters, okay, where we call them lactones, amides are called lactams, okay, and the nomenclature is very much the same, which means that if you say you have alpha beta lactam, it means you have 2 carbons other than the carboxylic acid one, okay, or the carbonyl one. So that's how it goes. So 1, 2, 3, if you were to do the IUPAC nomenclature, so 1, 2, 3 means that you have 3 carbons, and that includes the carbonyl, okay, in there. So these are called lactams, all right, and lactams and lactones are commonly found. That's why we talk about them. Otherwise, we wouldn't be mentioning them to you over here. Okay, and so this one here is a 6-lactam or an epsilon lactam. Amides don't smell that much. Amides are tame, very stable, very nice compounds. And then, of course, we have the nitriles, which is a little unusual, as I said, because there is no oxygen in there, all right? And so in inorganic chemistry, we call the the CN group as a cyanide, but in organic, it's called nitrile. Get it? Inorganic, inorganic. It's a little weird. Anyhow, then to name the nitriles, you would remove the oic acid and replace it with nitriles. So for example, if you have 2 carbons in there, it would be called ethane nitrile. Okay, ethane coming from the 2 carbons and the nitrogen giving it the nitrile, all right? but the CN is giving the nitrile. However, the carbon here is part of the long chain, all right? So it's ethane nitrile. Acetonitrile would be the common name for this. Aceto, remember, is two carbon thing, and you've seen carbonyls before on this, but this is a little unusual, as we said before. Okay, then this one here is benzonitrile, all right, coming from benzoic acid, and then you have the nitrile group here. And then this one would be phenylethane nitrile. Okay, two carbons, and so you don't want to use this as a substituent, you want to use this as your base chain. Okay, so two carbons, ethane, and then on the second carbon right here you have the phenyl group, and nitrile is your functional group. So here are all the derivatives of the acids, and then here are some of the properties, okay, for you in a nice little table. So acid chlorides, they have no hydrogen bonding. There is no hydrogen in there. Okay, esters, no hydrogen bonding. There is no hydrogen there. None of these have hydrogen bonding except for amides. Amides have hydrogen bonding, and that too they will not if they were derivatives. Okay, which means if the hydrogens were not there, there would be no hydrogen bonding in there. So it's really important to know that there is no hydrogen bonding, because that is what's going to determine the boiling points and solubilities, okay, of these compounds. So acyl chlorides, for example, they have low boiling points, which means they all exist as liquids. Okay, they do have the high polarity of the carbonyl group. All of these actually are going to be liquids, all right, because of their high polarity. Some of them have a little bit of a lower boiling point than others. Again, amides will be the highest one, especially if it is NH2, okay, because of hydrogen bonding. Okay, so it depends on what kind of a functional group you're dealing with, what is the size of it, but most of the times they will be all low boiling point liquids, and they will be usually not very soluble in water. Only amides will be a little bit soluble in water because, again, of the hydrogen bonding. Okay, esters very slightly, not really soluble in water. Acyl chlorides are slightly soluble in water, but it's not because of the solubility, it's actually because of reaction. Acyl chlorides react very readily with water, as do anhydrides. So both of these are actually very water sensitive, so not because of solubility, but because of reactions. Okay, and then nitriles are not going to be very soluble in water. Regarding the odors of all of these, acyl chlorides are pungent. They're terrible. We have to keep them in the hood. They smell. Okay, the same thing goes for anhydrides. Okay, really bad smelling compounds. So we keep them in the hood so we don't have to smell them. But sometimes you do. In that case, careful. Esters are probably one of the best smelling compounds. They're all fruity smells. So any kind of a fruit you can think of, whether it's pineapple or peach or apple or grapes, whatever you can think of, that fruity smell is coming from esters. So all of these fruits, they have esters in them. So you can imagine how big the ester industry is, okay, as far as flavoring agents is concerned. All the Jolly Ranchers that we have, all the flavored drinks we have, they don't have natural esters in them. They're all synthesized esters, and that's how they get the flavor. Okay, so you don't really have to get apple smell from apples. You can actually synthesize that particular ester and get the fruity smell of an apple. So in any case, that is esters. Nitriles I'm not very sure of, and then amides have no odor because they are salts. Okay, remember acid plus base gives you amide, and so usually salts will not have much smell to it. So for this little topic here, you should definitely recognize all the structures, okay? One of the things that happens by the time you get to this point is you know almost all the functional groups, except for amines now, you know all the functional groups. The problem with all these functional groups so far is that there are so many oxygens. You have alcohols, ethers, aldehydes, ketones, acetals, so many going on. And then of course all these acids. So you have to be able to recognize the functional group and know whether you're dealing with an anhydride or you're dealing with an acetal. Okay, so be very careful in recognizing functional groups. You should be able to name the derivatives. I especially ask you for esters and amides. Acyl chlorides and hydrides, not so much, okay? But definitely for esters and amides, you should know. And you should be able to predict a little bit about the physical properties, for example, solubilities and so on, okay, for all the derivatives.